Most viewers see meteor showers as visual fireworks, but for an autonomous vehicle's camera and LiDAR, they represent a catastrophic signal-to-noise ratio failure. While humans instinctively look up at the buck moon or a shower to witness beauty, LiDAR sensors in self-driving cars can be blinded by sudden spikes in luminance that exceed their dynamic range. This brief explains why July 2026's celestial events are not just astronomical curiosities, but potential stress tests for perception systems designed for consistent daylight and darkness, turning the sky into a variable hazard rather than a static backdrop. To understand this threat, we must first look at how these machines actually see the world. Autonomous vehicles rely on LiDAR, which stands for light detection and ranging, and high dynamic range cameras to map their environment in real time. These sensors operate within specific photometric limits. They are calibrated to detect reflections from roads, signs, and other cars under predictable lighting conditions. When external light intensity changes faster or brighter than the sensor's integration time, it causes saturation. This is a technical term for temporary blindness, where depth data is lost entirely because the incoming photons overwhelm the detector electronics. Imagine trying to take a photograph of a dark room while someone flashes a strobe light directly into the lens. The image goes white, and you see nothing else in that frame. For an autonomous driving system, this momentary whiteness translates to a complete loss of spatial awareness. If the sensor cannot distinguish between a bright meteor streak or a reflection off the buck moon and a real object on the road, it may generate false depth readings. The vehicle might think there is a massive obstacle blocking its path when the sky has simply become too bright for the camera to parse correctly. This challenge of extreme lighting variations is not theoretical. It mirrors problems faced by robotics researchers working in unstructured environments like the lunar surface. Studies on autonomous-legged mobile manipulators designed for moon operations highlight that harsh, high-contrast light, without atmospheric diffusion, poses significant challenges to perception and control frameworks. On the moon, there is no air to soften shadows or diffuse sunlight, creating extreme contrasts between sunlit surfaces and deep craters. Just as rovers struggle with this intense visual noise on our nearest neighbor, Earth-based autonomous vehicles face similar risks when celestial events introduce sudden, intense light sources that bypass atmospheric filtering before hitting their sensors. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The core of the problem lies in a gap we can call context awareness. Current intrusion detection systems, such as those based on radars technology designed to flag data contradicting physical road context, are built with specific assumptions about sensor validity. These safety layers assume that if a signal is strong enough to be detected, it represents a real object. However, they cannot easily distinguish between a genuine obstacle and a lighting artifact without redundant sensing layers or more sophisticated AI reasoning. If a meteor shower causes a massive, transient spike in ambient luminance, the system receives valid electrical signals from its sensors that look like physical data but are actually just noise generated by light overload. Standard checks may fail because they cannot tell if the object is a car or a flash of starlight without additional context that isn't present during those split seconds of saturation. This creates a scenario where the vehicle's digital eyes are open, yet it effectively sees nothing useful for navigation. The system must decide whether to brake hard based on a phantom obstacle or continue moving while blind. In many cases, the safest engineering response is to trigger a fail-safe state, bringing the vehicle to an immediate halt until lighting conditions stabilize. This forces the car into a stop simply because the sky happened to change its brightness profile faster than the software could adapt. The stakes of this sensor blindness are compounded when we consider human supervision limits during partial automation incidents. As noted in safety analyses of systems like those tested on vehicles such as the Ford Mustang Mach-E, human supervisors often prove insufficient for rapid environmental shifts. If an autonomous vehicle encounters sudden sensor blindness due to a celestial event, the human-in-the-loop fallback fails if the driver's own vision is similarly compromised by looking at or reacting to the same sky phenomenon. When drivers look up to witness the buck moon or watch meteors streak across the July 2026 night sky, their peripheral awareness drops just as much as the machine's sensors degrade from glare and saturation spikes. The data on how hard it is for these systems to maintain accuracy under stress is stark. Research involving a team of 9 authors demonstrated that while intrusion detection systems achieved up to 99.9% accuracy in detecting standard intrusions, they struggle when physical context contradicts sensor input due to environmental anomalies like extreme lighting shifts. The study highlighted that distinguishing between real obstacles and artifacts requires processing power and algorithmic redundancy that current consumer-grade autonomous stacks often lack for transient events. A file submitted by these researchers detailed how a sudden change in luminance can bypass standard filters, forcing the system into an undefined state where it cannot guarantee safety without human intervention or a complete stop. This reframes the July 2026 buck moon and meteor showers from passive entertainment into an active engineering scenario. Viewers will understand that smart cars are not immune to physics. They have specific hardware limits regarding light intensity. The takeaway is that autonomous navigation requires robustness against all environmental inputs, including transient celestial events that can create temporary blind spots in a car's digital eyes, forcing the vehicle into a fail-safe state or requiring manual intervention during moments when human vision might also be dazzled. The engineering reality behind these systems shows us that intelligence is not just about processing power, but about physical constraints. A robot cannot think its way out of being blinded by light. It must have hardware designed to handle dynamic range extremes, much like a rover on the moon needs specialized shading and exposure control. Until autonomous vehicles can match this level of environmental resilience against all forms of natural interference, they remain vulnerable to the very stars we admire in the night sky. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.